All right, so very, very quickly. So actually, it looks, since there's only 4 people who wanted to see this, I presume you guys all know what momentum twist, the 4 people who wanted to hear it. Do you know, you don't need to know what the AB 1, 2 means and so on, right? Okay, fine. So let's just, so let me say it quickly. So the MHV, but the MHV one-loop amplituhedron. So here, all we have is external data z's that are positive in the sense of the positive Rachmanian, and we have just one line AB. So that's the kinematic space for the integrand anyway. And all we have is that AB I plus 1 is positive, and that this sequence AB 1, 2, AB 1, 3, up to AB 1n has 2 sign flips. Okay? And so that's it. That's the whole space. And we need to understand now. Now we don't even have a form in Z because k equals 0. So the only form is in AB. All right? So we can even think of these momentum twistors Z as locked external data, and we're interested in what is the space of all ABs for which this is true. Okay, now I could just do it purely algebraically here, but just to give some intuition for it, let me go back. And I told you that we got all these sort of sign flip statements by projecting things all the way down to 1 dimension. But let's just back up for just a moment here and talk about what it looks like in 2 dimensions. So again, the picture is that we have AB, which is a 2-plane in 4 dimensions. And my external data is just 4-dimensional, just the ordinary 4-dimensional momentum twistors. And so the question is, what do things look like when I project through AB? When I project through AB, I go to a 2-dimensional picture, right? All the external momentum twistors now become 2-dimensional, just 2-dimensional vectors. And the question is, what does it look like? Okay? So now, one thing that it looks like is that we know that in the 4-dimensional thing, because we know AB 1, 2, AB 2, 3, also AB 1n, not n1, is positive. That means that in the effective 2-dimensional picture, let me put little brackets here for that. 1, 2, 2, 3, up to all of them, 1n are positive. And so that means that now let me literally draw the vectors, right? So I have some configuration of vectors like 1, 2, 3, so on, right? This says that they're all winding around the same way. 1 to 2, 2 to 3, 3 to 4. The positivity of all these things says that all of these things are winding around the same way, with one difference at the end. N instead of n to 1, n1 jumps backwards. Okay? So all of these pictures look like a fish. At the end, they go to like 1 to n, and then n jumps back to 1. Okay? All right, so that's what the configuration of vectors looks like. But the claim is that you're in the amplituhedron. I mean, you could wind around like this crazy ways, any way you like. The claim is that you're in the amplituhedron if this picture has winding number 1. Okay? Here's the origin when I project through it. If this picture has winding number 1 when it goes around. Okay? So it doesn't have to. So in the most simple case is n equals 4. Okay? 4 particle scattering. And so I could have 2 pictures. Here's the origin. So here's picture number 1 is 1 to 2, 2 to 3, 3 to 4. Oops. Okay, so here's fish 1, 2, 3, 4, and 4 jumps back to 1. That's one picture. But I could also have 1, 2, 3, 4. Yeah. 1, 2, 2. Sorry, what am I doing wrong here? 1, 2, 3. 1. Yes, exactly. Sorry. Yeah, it's fine. 1 to 2, 2 to 3, 3 to 4, and 1 to 4. They're all going around the same way. Okay. And the origin is outside. Okay. So this thing has winding number 0. Oh, 1, sorry. And this has winding number 0. So this, we claim, never comes from the amplituhedron. Okay? Whenever you project through AB, when AB is in the one-loop amplituhedron, in this picture, you go around and you have winding number 1, and not 2 or 7. Okay, so 1, and 1 is the maximum winding that you can possibly have. Now, let me tell you how this picture is related to this statement. And you can see it here, because what does it mean? So let's say that we project through 1, okay? Projecting through 1 means that we draw this line, and we imagine looking at the picture in the direction 1, okay? So if I project through 1 and I look at the rest here, like 2, 3, 4, you see that 2, 3 crosses a line, 3, 4 crosses a line. Those are my 2 sign flips. If I have something more, whereas here, what would happen if I projected through 1? I go 2, 3 doesn't cross, 3, 4 doesn't cross, 4, 1 doesn't cross. Okay? So I don't have 1. 2, 3 doesn't cross, and 3, 4 doesn't cross. So this would have 0 sign flips. Okay? And you can see how that's true more generally. So if you have so if we have any picture that has winding number 1, okay, and I project through 1, then it crosses it twice. Okay? Whereas one of these things would crosses it 0 times. Okay? So there's a 2-dimensional picture where you talk about winding number, and there's a 1-dimensional picture where you talk about sign flips. And the 1-dimensional picture is the kind of most primitive one, but the 2-dimensional picture is also nice for giving you some intuition. But let's actually, in this case, just go back to the 1-dimensional picture. We can draw it 2-dimensionally as well. And I want to say, so this is all I want. I want to find the space where these guys are positive, and this has precisely 2 sign flips. Now, because I start with AB12 and I end with AB1n, and AB12 by assumption is positive, and AB1n is positive, then no matter where AB is, no matter what it is, there has to be some place where this changes sign from plus to minus, and some place where it changes sign back from minus to plus. Right? So let's call this first place where it changes from plus to minus I. The next one is I plus 1. And then the place where it changes back, J plus 1. Okay? So first of all, that's how an I plus 1, J plus 1 enters this problem. Okay? Is that there's a place where the sign flip happens. And no matter where you are in the amplituhedron, there has to be some I and J for which this occurs. Furthermore, in that region of the amplituhedron, regions with different I's and J's are clearly non-overlapping because they're distinguished by these sign flips. Okay? So we just triangulated the amplituhedron in this case. The amplituhedron is completely covered by regions where the sign flip occurs at these locations, I plus 1 and JJ plus 1. Okay? So all that's left is to figure out what AB looks like when this sign pattern is realized. And remember, what's special here is 1. So we're doing AB1, blah, 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 blah. Right? Okay? So the claim, and we can verify this claim very easily and actually discover it. But the claim is that on this configuration, but it's also kind of easy to guess, right? It's easy to guess because in this case, you see this was the one-loop amplituhedron where we think about AB as a line. This is also the usual tree amplituhedron if we think about AB as Y and M is equal to 2 rather than 4 for the ordinary amplituhedron. So that means that we also know ahead of time what the triangulation should look like. It should be built out of positive matrices for G2n. Okay? So in other words, I should be able to write Y as C dot Z, where C is a positive 2 by n matrix. Okay?
Is this a general picture that you can reduce this loop and amplituhedron, this clean?
No, it's not. It's not. I mean, there's a piece of it which is like that always, though. I can say a little bit more about that in a moment. But let me just say that what you find is that the Z for A is Z1 plus some alpha Zi plus beta Zi plus 1. And ZB looks like minus Z1 plus gamma Zj plus rho Zj plus 1, where all of this alpha, beta, gamma, rho are positive. Now, what do I put all these funny signs? It's because I know ahead of time that I need to write this as a positive matrix. So it's going to look like an alpha and a beta and a gamma and a rho. And so if I put a minus sign here, then all the minors and everything else here is 0. Then all the minors of this 2 by n matrix are positive when alpha, beta, and gamma rho are positive. Okay? So what's very easy to check, you see the reason it's very easy to check is that this sign pattern is exactly telling me this sign pattern is exactly telling me AB 1i is positive, AB 1i plus 1 is negative, AB 1j is negative, AB 1j plus 1 is positive. But when I expand A and B is 1 plus something I plus 1. And when I expand A like that and B, so AB is a line, right? So I can always expand. Since it's a line, I can label it. I can label the line by where A is there's some plane 1 I plus 1, and there's some other plane 1 j plus 1, and I have some line AB, and I can label what the line is by where it intersects the plane 1i plus 1 and where it intersects the plane 1j plus 1. So I can call one of them I and the other one j. Okay? Sorry, I can call one of them A and the other one B. So that means that A is expressible as Z1 exactly this, and ZB is expressible as exactly this, and here we're not making any assumptions at all. Like wherever AB is, we can write it like that. But we have precisely these sign patterns. That's what we're looking for. And these sign patterns just tell us immediately that alpha, beta, gamma, rho must be positive. Okay? We just shove it in, right? These just actually calculate alpha, negative, beta, gamma, negative, rho. Right? So they exactly tell us that those are the sign patterns. And so we see that in this part of the amplituhedron with this sign flip pattern, A and B are immediately parameterized in terms of positive variables. So we know what the canonical form is. The canonical form in this region is just this omega for this place where the sign flip happens at ij is just d log alpha, d log beta, d log gamma, d log rho, which is exactly d log AB 1i over AB II plus 1 d log AB 1i plus 1 over ABI I plus 1, and then the other ones. Sorry for the messy writing at the end here. And we're done. Okay, so this is the whole amplitude. The whole form is just the sum over ij of this omega for ij. Okay, so that's how the sign flip immediately triangulates the space, and it gives you the integrand. Okay, the only thing that's left is to, if you want, to expand out those d logs and recover that explicit Kermit formula. But that's a simple exercise that I'll leave for you. By the way, I hope from this picture, those of you who are old enough will understand why it was called a Kermit. This looks like Kermit the Frog. Okay, so that was the reason. Yeah.
You take this three-amplitude amplitude form and replace some variables by this.
Yes, in this case, well, so here's the general story. The general story is that for general k, so let's say you're doing things at one loop, then the general story is that we have a k plus 2 plane YAB. Okay, so we have y and we have AB. So the y is a k plane, AB is a 2 plane. So we have a k plus 2 plane YAB and a k plane y. So we can take the k plus 4-dimensional external data and project it through the k plus 2 plane. From that point of view, the k plus 2 plane YAB is like the tree amplituhedron, but for the m equals 2 problem.
Yeah.
Right? So so that composite YAB, that k plus 2 plane, must be in the m equals 2 amplituhedron.
Yeah.
That's what these rules say. From this point of view, you have a k plus 2 plane with a special k plane embedded in it, y. Okay? So that k plane that's embedded in it must be in the tree m equals 4 amplituhedron. So the loop amplituhedron, the one loop amplituhedron, is actually the intersection of two different tree amplituhedra, one for m equals 2 and one for m equals 4. Okay? So you have the m equals 2 k plus 2 amplituhedron with the k plane inside that k plus 2 plane living inside the tree m equals 4 amplituhedron. And that's the one loop problem for any k.
So basically with, you have...
So for example, if yeah.
You have an intersection of two positive geometries.
Yes, yes.
And and I suppose that there is a formula that relates this intersection is also positive geometry, yeah?
Yes.
So basically what you are saying that your answer can be expressed in terms of three forms.
Yes, this is actually a really cool thing. Exactly what you're saying. Exactly what you're saying is a formula that we have been too lazy to write down. We should really write down because it's a really novel formula. So let me talk about the first interesting example. It's for k equals 1. It's for NMHV. The standard way of thinking about k equals 1 NMHV amplitudes from recursion relations from anything is roughly speaking, precisely speaking, a 4 form times a 4 form. Okay? There's a 4 form for the loop integrand part, and there's a 4 form for the R invariant part. Okay? So the whole thing is an 8 form, but it's kind of naturally divided into a 4 form times a 4 form. That's in the usual BCFW recursion relation type picture. In this picture, it's naturally a 6 form times a 2 form. Not a 4 form times a 4 form. And it's precisely because of this business about it being an intersection. Because on the one hand, you have, so what is the geometry here? You have a YAB, which is a 3-plane in whatever we're in. 3-plane in 6 dimensions, 3-plane in 5 dimensions, okay? So when I project through YAB, I have to go down to the m equals 2 amplituhedron. So this 3-plane YAB has got to live in the m equals 2 amplituhedron, and so there's a 6 form that goes along with him. But y itself, living in YAB, has to live in the is now a point on this projectively is a point in a two-dimensional plane, and that point. So what is a geometric picture? Let me say it again. We have YAB, which is a plane. Okay, it's really a two-plane, and so I have this two-plane sitting in 4 dimensions. Okay, so a two-plane in P4. Okay, so the m equals 2 amplituhedron tells me something about a form for this two-plane in P4. But on top of that, y itself is some point that's moving along on this two-plane. And this two-plane cuts through the usual cyclic polytope, right? So it cuts through the usual cyclic polytope on some shape, some polygon. And the canonical form for y is the 2 form for that polygon. And so the answer should be expressed in terms of some triangulation of the m equals 2 amplituhedron, and inside each part of that triangulation, it should be further divided up into what it looks like when that plane cuts through the usual cyclic polytope. So the answer should come out in this intersection picture should not come out as 4 form times 4 form. It should come out as 6 form times 2 form. And it would be wonderful to do it. I mean, yeah, we have not done it. So we suck. So we should do it. Yeah. Huh? Sorry. Huh? Yeah. Speak for yourself.
So
Yeah.
all
Right.
the stuff that you have discussed before that
Yes.
is a building construction.
It's sorry?
It's a building construction. So you really, you can forget everything that you have explained us before, with all this winding and so on. This picture.
No, because the winding business or the sign flip business is the I mean, it depends what you want to forget it for. So if you want to, yeah, yes.
So I would like to calculate the amplitude.
Yes.
And I do not, and I will believe you everything that you will say.
Yes. Yes.
So then probably you can describe for me this what your description was. Did not refer any to the winding, to anything else.
Oh no! So those are two different. I mean, so you could. So there's both calculation and conceptual things about the winding stuff. It's by the way, it's conjectural that it's the same as the usual picture of the amplituhedron. It's just it's been proven in some cases and checked in many examples. But I just want to just to back up. I want to tell you. I mean, this is not an unusual thing that we're looking for. For polytopes, you're very familiar with the idea that there is the description of the polytope that's centered around the vertices, the notion of a convex hull. That's one idea. But there's another idea which cuts out the polytope by giving you the linear equations that cut it out. So that exists for polytopes. Amplituhedra are just Grassmannian generalizations of polytopes, and therefore it makes sense to look for both the descriptions for amplituhedra, right? The old description is the analog of the convex hull. The new description is the analog of the cutting it out with the inequalities. But on both cases, there was some extra decoration that was needed. For the amplituhedron itself, the notion of positivity in the positive sum had to be replaced by positive Grassmannian, and in the description in terms of the faces, the equations that cut out the faces, it had to be supplemented by these winding topological considerations. So you can, purely as a definition of the amplituhedron, you could take either one. We haven't proven that they're equivalent to each other, but it seems to be true. What's missing is the analog of what for polytopes is called Farca's theorem, which is this relatively trivial but not 100% trivial statement that given a bunch of vertices, if they have a convex hull, they're also cut out by a bunch of linear equations. So you can go back and forth between the descriptions. So the analog of that is all we've done, right? In this winding business, is just find the analog of the second way of doing things. But purely if you want to think about the amplituhedron, you could think about it either way. And however you want to attack the problem, either from C dot Z or this other way, is equivalent. There's this extra thing that this second way allows us to talk about everything directly in momentum twistor space. So that's yeah, right, yeah. And so yeah.
Really, I think that both of these descriptions are really concrete descriptions.
Yes.
And what we really need, we need positive geometry, which is that doesn't depend on description. Can be given this way.
But it needs some description. I mean, I agree that there's no a priori reason to privilege one or over the other. But well, just to give you an example, what we just talked about, this was like a few line calculation of this amplitude. This was not available in any other picture of the amplituhedron. If you want to talk about it in this way, in the C dot Z way of talking about things, you'd have to show that the image of these cells covered the amplituhedron, and it's not, I mean, actually we had done it a long time ago, but it was kind of laborious, precisely because it's hard to check whether things are in or out and where they are, right? Whereas here we're just done. We wrote down the sign patterns, we're just done, and we just triangulated the space. So the second description in this case was much more rapid. If you watch some of the, either come or watch some of the talks from the Amplitudes conference next week, we'll give another example of this kind of thing, where keeping track of the sign patterns lets you calculate certain aspects of amplitudes to infinite loop order. So, so those are things that you just cannot do any other way. So it's useful. But I agree with you. I think it's not clear we have at all the most intrinsic description even yet of the, I think all we've done is finally make it more symmetrical between finding all the analogs of the usual stories for polytopes. But the thing that I didn't have a chance to talk about at all, which that I could talk about till like 4 a.m. tomorrow, I could talk about ad infinitum, is the question of the existence or not of a dual to the amplituhedron. And that is a thing which is really missing. That's the thing which is the thing that exists for polytopes that we would desperately want to have for the amplituhedron, and we still don't have. I think that's probably the hardest of everything, and the most important notion of everything. And let me just say this very, very, very quickly. I won't go to 4 a.m. for it, but since you guys have seen so much of this already now, there is this fact that we can see for the canonical form. I actually did two things. If you take so we saw that the canonical form for a triangle was 1, 2, 3 squared. There's the y, d squared y. And then there's a y, 1, 2, y, 2, 3, y, 3, 1. OK, so that's one formula. Then we talked a little at some different point about a different formula, where you give me some vertices x1, x2, x3, and there's some line at infinity, I don't know, let's call it I, and we give a formula for the area of a triangle that was just x1, x2, x3 over x1 dot I, x2 dot I, x3 dot I. So this is a great formula if you're given the vertices of a triangle. But what would the formula be if someone gave you the edges of the triangle? Okay, so if someone gave you this edge, let's call it A, that edge B, that edge C, then let's continue with this formula over here. Then what I would have, x1 is really A intersect C. x3 is C intersect B. x2 is B intersect A, and so on. So the numerator would be A, B, C squared And the denominator would be this line at infinity AB, line at infinity BC, line at infinity CA. Okay? And so now you notice a very interesting similarity between this function that shows up in the canonical form and this formula for the area of a triangle given in terms of the edges rather than the vertices. Okay? So again, to make the connection precise, take this picture, y 1, 2, 3, and take its dual, where I interchange points with planes. So in this dual, y becomes points with lines. In this picture, y becomes a line. There is a line out there. And 1 becomes a line, 2 becomes a line, 3 becomes a line. And so I have a picture of a triangle where this is the edge 1, 2, 3. And now the area of this triangle, of this dual triangle, with y as a reference at infinity, is exactly equal to that function that sits in front of the canonical form, where y plays the role of infinity. You see, this is exactly the same as that formula. Okay? So this is a remarkable connection, that the form with logarithmic singularities on some positive polytope, we'll immediately generalize it. Okay, so this depends on y, but this is equal to y d ny times the volume of the dual polytope. The dual, where you interchange points with planes and planes, you just dualize the polytope, where y is no longer a point, but is the reference plane at infinity. Okay?
So I didn't
So,
quite understand
yeah.
The statement.
Yeah,
Yeah.
the statement is that,
The form.
yes, here we have a form.
By volume of the.
That's right. But so a form is this universal thing, form multiplied. This function has weight minus n in minus n and minus 1. So let's do this example again. Okay. So let me write it again. So here is a.
So in this form, you have dy.
That's right. That's right.
How dy dualizes?
I'm not dualizing it. That's what I'm saying. The volume is just a number. Okay. So yeah, the volume is just a number. So I start with this picture again. This is the original picture. Y is a point. My data are points. Okay. And I'm saying that the form is equal to y d squared y times, in this case, times the volume or the area of the dual picture. The dual picture where I have 1, 2, and 3, and y is the plane at infinity.
Yes.
Yes.
The coefficients.
Yes, that's right. Exactly. Yeah. So a more fancy way of writing this is that the volume can be written in a nice projective way. The volume of a polytope, any old polytope, in this case the dual is what we want, with y as the plane at infinity, can be written as an integral. It's a volume, so an integral over points in the dual polytope of the universal measure on the dual divided by w dot y to the n plus 1. And that looks like a funny factor, but it needs to be there by weights. And if you just set y to 1, 0, 0, 0 like we normally do to infinity, this is just normal volume. Okay? So the remarkable formula in the end is that a canonical form for a polytope, a canonical form for the polytope P that depends on y is the integral. I mean, in the end, there is this sort of simple universal form on the product of two spaces, the space and its dual, divided by w dot y to the n plus 1, where w is inside the dual of the polytope. Okay, so this is the the remarkable formula. This formula explains many things, okay? All the properties of canonical forms, including the fact that it has logarithmic singularities, including that it has this additive structure, everything we know and love about the canonical forms is explained by the existence of this dual, the polytope and its dual. And in fact, there's one master form, this sort of trivial one, on the whole big space. And we can integrate over the dual of the polytope, and we get the canonical form for the polytope. We could go the other way around. We could, everything you might want to know about canonical forms for polytopes is contained in this formula, okay?
This is what you mentioned about tomato polylopes, right?
Sorry?
This is what
yes, exactly. That's right. Yes. So I mean, exactly. There's lots and lots of things that have this basic structure. Let me mention one. Sorry, I'll come to your question. I want to mention one of many things that this makes obvious. Is that when y is inside the polytope, the canonical form up to this factor, if I strip off this factor, is a positive number, right? I mean, it's a volume, so it's positive. Now, I want you to notice that this fact is totally unobvious from the triangulation picture. Okay, so if I take the polytope, so just let's say I have a square, and I triangulate like that, then I'm writing it as a sum of two pieces. But let's say y is in here. Then this piece is positive, but that piece is negative, numerically, right? But the sum of the whole thing is actually positive. And in fact, it's a peculiar thing. For the polytope itself, let's say I add an extra vertex, so I'm making the polytope bigger. Then the canonical form actually gets smaller, right? Because, I'm adding yet another piece which is negative. Okay, so if I keep y inside here and I just add more and more vertices, the polytope gets bigger, but the coefficient of the canonical form gets smaller. Well, all of this is obvious from the dual picture, because in the dual picture, I start dually of the square, and then when I add a triangle here, I'm lopping off a triangle there. When I add another one there, I'm lopping off another triangle here, and so on. Okay? So this picture makes it obvious that the final answer is positive. This picture, it's not obviously positive, but they add up to being something. Positive. Okay, so this for polytopes is a very important formula, and we don't have and have not had unsuccessfully searched for the analog of this formula for the amplituhedron. And people who have worked a little bit on the amplituhedron, there are many different aspects of it, and everyone who has touched some part of the subject has run into the desire to find this thing from one point of view or another, and everyone runs into the same kind of nonlinear obstruction. Okay, so you can derive all these formulas. I don't have time to explain it, but all these formulas are really straightforward from any description of the amplituhedron. You write the Grassmannian formula as dc over c. You start from that description, you do some very straightforward manipulations of delta functions, Fourier, Laplace transforms, and poof, you move around and you get to the other ones. And sometimes the stories are very pretty, they're all very nicely connected to each other, but they're all very commutative and linear. I mean, there's nothing, in the end, you're just dealing with these dc over c's, and that basic simple structure is all that's going on. When you attempt, for example, to begin with the Grassmannian integral at higher k, where it's really amplituhedronic, and do the same things, the Fourier transforms become nonlinear, and you can't do them. So okay, you say, fine, that strategy doesn't work. You try many other strategies, and it's always the same nonlinear obstruction over and over again. Yes?
So what is the general statement? So if you have this polytope,
yes,
which is divided into pieces,
mm-hmm.
What happens with dual polytope?
If you divide the polytope into pieces, the dual polytope is triangulated, but in an inclusion-exclusion way. Okay. So for example, let's do a little example. So already this is a nice example actually. So let's take quadrilateral. Let's just take a quadrilateral. So where the vertices are 1, 2, 3, 4. and I triangulate it to these two triangles, okay? Now, let's see what's happening in the dual. In the dual, I have 1, 2, 3, 4, and these are now lines. See, I always draw the damn quadrilaterals with parallel lines. Okay, so now I have 1, 2, 3, 4. Okay, now here I had this new triangle here where one of the edges was 1, 3. Okay, so that means in this picture I have a new vertex, which is that 1, 3, right? So this is the vertex 1, 3. And so this triangle is associated with that area. This triangle is associated with that area. Okay? And so you see this picture, this plus that, is reflected in the dual as that minus that. Okay? So it adds points on the outside and is some inclusion-exclusion thing. Okay? But the final answer is always positive, right? Now, something that Yara and Andrew Hodges and I checked many years ago is that if we take all these canonical forms for the amplituhedron, they're miraculously always positive in the same way. They're written as a sum of huge numbers of positive and negative terms, and they always add up to something positive. Okay? So that's that's something that's very mysterious that would be obvious if there was a volume picture. Okay? We don't have a volume picture. So it's not obvious. It's not obvious this is right. But this idea is very important, and it surely has some Grassmannian generalization, some amplituhedronic generalization. And I think it's a big, important, outstanding problem to figure out what it is.
Is it true that both original polytope and dual polytope have positive geometry?
Yes. Polytopes are always positive geometries.
No, this is really
Yes.
this,
Yeah.
That's really this, you relate to positive geometry.
Yes, very much so.
So but here you do not take this canonical for dual polytope.
No, we're not taking the form for the no, we're not, but in a sense, it's something a little more basic. We have one form, very natural simple form, that's defined on the product of the two spaces, the space and its dual. We take this sort of very simple canonical form of the product of the two spaces, and if we integrate the form on one space, we get the canonical form for the other. Huh?
But the form you integrate over...
Yes. No, it's not a canonical form. It has these high powers. It's not a canonical form. No. But it's the only form you can think of to write down on the product space, right? I just have the space of points and dual planes. So I need to have both of these factors, and by weights I have to have something else. There's nothing else that makes sense to write down. So this form is, I think, as God-given as you can make it. And now you want to make a form on Y, you should integrate over W. And you integrate on the dual of the polytope, you get the canonical form for Y. You could integrate over Y, you'd get the canonical form for a W.
And the conjecture is that for any positive geometry, you have dual positive.
That's the dream. Yeah, we don't now. It's we've gone slightly beyond polytopes. So there are, for example, for G2n, we have versions of this formula. We have kind of interesting versions of this formula. So they do involve integrals, but they have a slightly fancier structure. What else? I think actually that's our only example. Sorry, that is our only example. We have a that's right. We have things for the NMHV bar, but that's basically the same as k equals 1. And then we have a very different story for a dual of the positive Grassmannian. So that's something we've had lying around for a year and a half now, but we don't quite know what to make of it. It's very different than any of these things. So I probably shouldn't. Yeah. It wouldn't make any sense for me to talk about it right now. But
positive Grassmannian, in some sense, has a dual trivial way.
Yes, but that's so. Let me tell you what the purpose in life of these duals is, right? And you see what the challenge is. What you want is some object whose facet structure, whose vertex structure captures the facet structure of the thing that you want. And you see already what the challenge is, because for example, the simplex, so you want to start with the simplex as the simplest thing. Simplices are self-dual. Great. Now, the positive Grassmannian is the simplex of the Grassmannian, right? That's the simplest thing in the Grassmannian. So take the first case, positive G24. Okay, its facet structure is not self-dual. It's a 4-dimensional space. It has 4 codimension 1 boundaries. It has 6 0-dimensional boundaries, okay? And in between, it doesn't look anything, I mean, it's definitely not self-dual in the standard way. So then you can ask, what could you look for in the Grassmannian that would have 6 boundaries at codimension 1, just to get some idea of something that might look like the dual? And it's very hard. It's very, very hard to come up with natural spaces like that. So it's not obvious what we should be trying to mimic, what we should be trying to generalize. This is a thing that we would most like to generalize. And I can tell you something interesting about it. You can definitely take this formula and naively generalize it to the Grassmannian. No problem, okay? What happens, though, is interesting. You see, when you do this integral, I mean, it's not super obvious what you should get in the end. Well, maybe here it's not so bad. But you're integrating something that seems to have some nonlinear stuff here. You know, how do you know that you're supposed to get some rational form in the end? But you get a rational form, okay? When you do this on the Grassmannian, so I mean, let me be very, very concrete. So, you know, I can say I want to integrate these forms on the Grassmannian. You can write as ABD squared A, or anyway, there's some analog of y dy dy. So y1 y2 d squared y1, y1 y2 d squared y2, and then the dual analog, just like you said, w1 w2 d squared w1, w1 w2 d squared w2, over, and then just y1 y2 w1 w2 to the fourth, yeah, okay? And now where w12 lives inside positive G24. That's what the dual looks like. Okay, so that's it. So that's perfectly well-defined thing. You can do this integral. The problem is it's not rational. It has a logarithm in it. There's no reason ahead of time it had to be rational. It's not rational. So is it good, bad? There's a sense in which there's a rational piece that you can extract out of this thing with the log. The rational piece is correct, gives you the canonical form. Okay? But the answer is not rational. So that's something that we've played with for a while, to see if there is some way of extracting these rational pieces underneath the transcendental ones. But it's but already these are some of the sort of things that go wrong. So every naive extension of this either has something wrong, you can't do it, or has something unusual that you weren't used to. In this case, we get a log.
There is a paper by Lauren Williams where some duality between Grassmannians is considered, but I believe that this is completely different.
Yeah, I mean there are really simple things like Gale duality. There are things like that, but like k to n minus k and stuff like that. That's not what yeah. Right.
They are proving that this trivial duality that you have mentioned, I believe that is related to mirror symmetry.
Oh, that sounds good. Right. Right.
And basically, they relate, I believe, a cluster structure with X cluster.
Well, that sounds like something that we want. Yeah.
Do not
right.
quite remember what happened.
I have to say, let me say, but since we're talking about this, and let me just say one more thing about this. So this is such a big fantasy that the sort of chances of working are, I don't know, I think chances of working are, I won't say that they're very low, but it's a big fantasy. There's nothing other than fantasy about it right now. But let me just say it anyway. So don't laugh. You know, this is the kind of fantasy you need to have. I don't know what kind of fantasies you're expecting, but this is this is the life of a theoretical physicist, my friend. You know, what do you want? Riches, glory? No, you want the dual amplitude. You know. Okay, so here's the chain of things that I would give a lot to see. So we have a picture of the world with gluons, and we're talking about gluon scattering amplitudes. And somehow there is the amplituhedron, at least for n equals 4 and so on, which for the integrand and for all the other things we would say about it is clearly related to the physics of gluons, right? Now, by which I mean there's nothing that looks like gluons, there's nothing that looks like local evolution, blah, blah, blah. But the formulas you get are the formulas you would have gotten for gluons, right? It's just you're getting them in some totally different way, okay? Now, purely from the internal desires, modulo Mr. Fun-making here, right, of thinking about the amplituhedron, we want something here which is kind of a dual to it. So we want the dual amplituhedron, okay? And this duality, if it exists, you know, this connects to Desargues and the 1500s, right? This is some kind of vast 21st century generalization of point-plane duality. That's what we're after. Okay? So this is something purely internally within the mathematical desire of understanding canonical forms in some nice way and so on in the story of the amplituhedron. But what could this, I mean, everything is symmetrical. So the amplituhedron is related to gluons. What could this be related to? It has to be related to strings, okay? This should be the origin of the gauge-gravity duality, right? So that's the fantasy, right? And it's not quite as absurd as it seems at first, because this formula has another name. The formula I just told you for the area. So actually, let's write this formula again, and if we keep going, we'll turn into spherical contours. But this formula. So the formula for the area of a triangle. So let's write that formula again. So if you give me this x1, x2, x3, let's say, over x1 dot y, x2 dot y, x3 dot y. This is the formula for the area. This is the area of the triangle. And we say that we can write this as the integral of some x d squared x over x dot y cubed, where x lives inside this triangle made from x1, x2, and x3. Okay? So again, that was the most basic thing, the most basic representation of a canonical form as an integral, right? But this formula has another name. How many of you recognize the name for this formula? Sorry? It's the area of a triangle. Sorry, but this identity. But what does this identity remind you of? Something with 3 poles that you write as an integral of something where you get a cube power downstairs. It's Feynman parameterization. Okay? Okay. Feynman parameterization is nothing other than the formula for the area of a simplex thought of projectively. This is yet another great advantage of projective thinking. Okay, so what does this mean? This means that, let's go back to the amplituhedron, that if there is a dual amplituhedron, then the formula for the canonical form is given as an integral of the dual amplituhedron. Those dual variables are like some version of Feynman parameters. Okay? And that would be the whole point, especially at loop level. You see, the dependence on y here is complicated. The dependence on y here is simple, right? That's why we do Feynman parameterization, so that we can then integrate over the loop variables. Well, it'll be exactly the same with the amplituhedron. If we had some loop, if we had some dual for the amplituhedron, then we would write the forms as an integral over this dual space. The dependence on AB would be trivialized, and then we could just integrate over AB to do the loop integrals, and we'd be left with an integral over the dual amplituhedron. And that would be the final answer, the final integrated answer, not just the pieces, right? So that would really be great, because when we normally do loop integrals, we one way or another, break up things into pieces and sum them differently. This would give you a natural geometric object that combines everything together. Now for the amplitude itself, not just for the integrand. And why does this have a prayer of being related to strings? Because there's been this ancient picture going back to the 70s that when you go to strong coupling, what's going on is the Feynman diagrams condense into the worldsheet, right? I mean, that ancient fishnet picture that the Feynman diagrams get denser and denser and eventually turn into the worldsheet, that's been understood in various contexts, matrix models, in various places. There are limits where you can see that happening, but not for a realistic theory, like a realistic gauge theory in 4 dimensions, right? So if there was a hope for seeing in some rational way strings emerge out of the gauge theory, that was always a sort of reasonable path. And actually all the cool stuff that's been going on recently with resumming these fishnet diagrams and so on, seeing this interesting structure show up when you look at the fully resummed answer, I think there's some indications there that indeed there's something. I mean, there's something nice about that class of diagrams that might be related to something stringy. So that's the hope. The hope is that the dual amplituhedron is like the smart Feynman parameterization. It's the correct way of thinking about Feynman parameterization that allows, when you go to strong coupling, to see this picture, this old picture of the fishnets condensing into the worldsheet to emerge. So anyway, this is a very large scale fantasy. I have no idea if the probability of success of 10 to the minus 500 or 50%. But if it's true, I think it would be the coolest story that the newest fangled duality is directly connected to the oldest duality we've ever seen in this very, very direct way. Okay? I think that would be totally, totally awesome. But that doesn't mean that it's true. Yes, you had a question many times. Yeah.
Yes.
Right.
In the original amplitude, the one from equal 4, like Feynman diagrams are nowhere to be seen.
That's true. That's a big problem, actually. And the hope is that the dual amplitude would help with that too.
Okay.
So
by cubic by joint.
Yes.
One loop.
That's right.
I thought if, like for example, with this halohedron, the sum of the Feynman diagrams.
Well, you see it very clearly in your definition, right? That's right.
Of the dual version. We can see.
Well, I mean, sorry. Thanks for bringing this whole thing up because. So this I've said these fantasy words for many years, and it's not so clear concretely how to go about trying to find this, but it's an extra big motivation to look for the loop level version of the geometries for isosahedra and the biadjoint theories like you've been looking at one loop and at higher loops, because if they exist, they're very likely polytopes. Okay? And if they're polytopes, their duals are polytopes, and so we can study them. That's the sort of big problem with the amplituhedron, is that this is already a very fancy object, and it's dual, we don't know what it is. But we might be able to make more progress on this general question by doing it in a context where we can hope to figure out what the geometries are at loop level and hope that they continue to be polytopes. So if there's some kind of loop level icosahedron at all loop orders, then I would be shocked if it's not a polytope of some variety. But, maybe it has funny higher genus or something, but it should be more understandable. And then that would be spectacular if we could then take that, find the analog of its dual, and then see if this fantasy or some version of this fantasy could come true for that example. But I'll just say one last thing about this is that there's still to me a kind of a difference between the kind of picture of the amplituhedron and the story of the icosahedron. They're very, very parallel, with one difference, which is that's still the kind of introduction of how you see this icosahedron geometry. It still has, to me, it still has a whiff of human interference in it and human desire, right? So you say you want to find this subspace, you find this clever combination, and we can say lots of words, why it's natural, why it's great, why it's inevitable, and all those things, but I don't myself fully believe them, okay? It's very natural, but it's not quite as, this has just some sort of perfection to it. You cannot change it, you can't mess with it, and once you go down this path, honestly, there's nothing else you can do. And part of the indication is that the transition from tree to loop is kind of, you just keep going. There's nothing, once you start doing this, you can't do anything else. So I'm hoping that, but there's enough rigidity in the icosahedron story that it could just be that we haven't found exactly the right, well, anyway, I'm not saying anything particularly useful, but I would get much more convinced that that has a similar perfection if we find an all-order loop story soon, right? I would be disappointed if the loop story is that if it looked kind of like higher and higher genus surfaces and we have to engineer it order by order. That's not the picture for the amplituhedron that just sort of tells you very quickly how to think about all loops at the same time as trees. So, but if an all loop order picture for the icosahedron, for the phi cubed biadjoint theory emerges, then I would drop everything and just work on figuring out what its dual looks like, just to see if there's anything to this fantasy. So
really, for three amplitudes, you can represent this three amplitudes as a sum over positroid.
That's right.
And the question is whether it is possible to represent loop amplitudes as a sum of over positroids.
It's not positroids. That's the thing. There is an analog of Playback graphs. There's an analog of Playback graphs. In fact, for momentum twisters, there's even a very effective and useful analog of Playback graphs at loop level that Song and our student Yuntao and other people worked out. So the analog of Playback graph, but it's not clear what the cells are. So part of the interesting thing is that at loop level, especially when you go to two loops and beyond, the structures in the Grassmannian that are associated with the loop amplituhedron are different. They go beyond the standard usual positivities. Okay, I can tell you what they are. So for example, even if you talk about things if we talk about things in the oldest description of the amplituhedron, we say that we have y equals c dot z, where c is in the positive Grassmannian. Okay. When you go beyond, and you have to find cells in this positive Grassmannian. When you go beyond the positive Grassmannian, you have to do a little more. For example, at one loop, instead of looking at a k-plane C, so you have a k-plane C in n dimensions, you also have to add some 2-plane D. Okay? And this 2-plane D is in the is in the complement of C. So I should so D is only defined by any shifts in the direction of C. Okay, so that's the bigger space. First of all, it's not just the Grassmannian. It's not just K by N matrix. It's the K plus 2 by N matrix, but with the property that all the minors are positive still. Okay, so all the K by K minors are positive, and the K plus 2 by K plus 2 minors of this matrix are all positive. Okay.
And the other minors are
Sorry?
positive? Are all other minors
No,
positive?
no, not. I mean, the ones that like span across this are not positive. They don't make sense because they're not invariant under the GL2 and the GLK. Right. That's right. Huh?
Invariant minors.
All the invariant minors are positive. That's right. That is the idea. Okay. Okay.
Even of the size K over 2.
No, all the maximal minors. No, not, yeah. Already for the positive Grassmannian, it's only the maximal minors that are positive. Not all the.
Really, if you have a Grassmannian matrix, which is
Yes.
Rectangular,
Yes.
you can extend this to square matrix.
Yes.
This positive matrix.
That's right. No, it's not. Yeah, you can do that, but. So I guess in that sense they would all be positive if you did that extension. But if you leave it like this, all the maximal minors of this matrix are positive. Okay, so that's already something novel beyond the usual positive Grassmannian. And then when you go to higher loops, it's the same thing. Then you have some D1 and some D2, another 2, and now the C are positive. C with D1 is positive. C with D2 is positive. C with D1 and D2 are all positive. Okay? So it's this extended positivity that you have to learn to deal with. And so while these guys know the Playbit graphs very well, what is not known is what the analog of the space is, right? And what the cell structure is and all of that stuff. I think the main thing which is known, I guess for k equals 1, I forget if it was k equals 1 or all k at one loop. But certainly for k equals 1, they have the analog of the top form, of the canonical form. The analog of this form with cyclic minors.
For all k.
That's for all k. Okay. For one loop, Song and Thomas Lamb and Yuntao worked out the analog of the canonical form in this case. And it was already quite interesting. But the cell structure, the analog of permutations, the analog of all of that stuff is not known. So this is the real. I mean, this is the real wilderness of the amplituhedron. Our mathematician friends are, they're starting to get some control, but even still not. But some understanding of the tree amplituhedron. But the story of the loops goes, I think a few levels beyond what we're familiar with. So.
Let me ask the following question. First of all, elementary question that I don't know precisely the precise answer. So it seems that Grassmannian can be obtained from simple blocks by means of amalgamation.
Yes.
So do I understand correctly that every diagram,
Yes.
gives you a recipe for amalgamation?
Yes. Absolutely.
So
Yes.
This is first question. But the second question, so really, what did you say that in this loop case, you have a kind of diagram?
Exactly. In fact, they're the same. They're the same, and they have one new kind of sort of object which does the loops for you. Okay.
So really,
right.
So really, this is it true that the same statement is?
Yes.
That you have.
There's absolutely a rule for amalgamation, and you can use their recipe to build these matrices. Okay. So that's they explicitly build these matrices. So that's great. That's why it's a good start. Right.
Amalgamation is a really very general notion.
Yes, absolutely. Yes.
Can be.
Yes. Absolutely.
Does it
Yeah.
agree with the standard Goncharov-Fox fiction.
Well, I mean, agree is hard to say because it has a new thing. I mean, the Fock and Goncharov picture is about, well, I don't know well enough to answer your question very precisely, but what I can say is that there is something new here. Like they don't just have just black and white vertices. They also have like a new object that represents the loops, right? There is some kind of puncture, right? That's right. Yeah. So, yeah.
For Goncharov surface doesn't contain this this black and white or something else. This is complete. This so really this is the stuff about cluster algebras, and you are joining cluster algebras.
Right.
And so the question is, can you embed this picture in cluster algebra picture?
I don't know.
In the information of cluster.
I don't know. For a variety of reasons, my feeling is no, but it's not a theorem. It's not close to a theorem. Yeah, I don't know. Yeah. Oh, we can take another break. Yes. Yeah. Right. Yeah. The what? What did you say?
Natural selection.
Natural selection break. All right. Okay.
Continue at midnight.
Yes. We'll continue at midnight. That's fine. Yeah.